Alright AI fanatics, let's kick things off with Rainbow DQN, the ultimate DeepQ network upgrade. Imagine the original DQN as a pretty solid robot, but it had some weaknesses. Enter Rainbow DQN. It's like taking that robot and giving it 6 awesome power-ups all at once. Think of it as the Megazord of DQN, combining double DQN, dueling DQN, distributional DQN, multi-step learning, noisy DQN, and prioritized experience replay. Each improvement addresses a specific challenge, leading to significantly enhanced performance for navigating complex environments. For example, double DQN tackles overestimation bias by separating action selection from value estimation. Dueling DQN splits the Q-value calculation into state value and advantage, providing clearer insights into the effectiveness of each action. Distributional DQN also helps by dealing with the distribution of returns instead of focusing only on the expected return, making the model more resilient to noise and fluctuations. The whole thing delivers more stable learning and superior performance. It's like getting a complete overhaul for your AI agent. This is perfect for games, simulations, or any setting where precise action selection is crucial. We're talking about a paradigm shift in DRL. Now, let's shift gears from video games to the volatile world of finance. Can we use DeepQ networks for something as unpredictable as Bitcoin trading? Absolutely. This isn't about some get-rich-quick scheme. It's about demonstrating the adaptability and power of DRL. Imagine an AI agent trading Bitcoin. It utilizes DQN to make buy, sell/hold decisions. It learns from historical price data, analyzing patterns and trends to develop a powerful strategy. This agent observes the market price as the state, its trading decision as the action, and whether it earned a profit or loss as the reward. The aim here isn't necessarily to predict the future price of Bitcoin, a very difficult task. It's about finding a trading strategy that consistently generates profits, even in a chaotic market. This is an amazing example of how DRL can be used to deal with real-world financial complexities, taking advantage of learning and exploration to optimize profits in a dynamic environment. It's a testament to the effectiveness of DRL in handling very dynamic situations. This application of DRL can really help us understand and potentially improve how we approach investment strategies. Think about how incredible this is, teaching a machine to profit in the often irrational cryptocurrency market. Next, we're going for an adventure, but not just any adventure. It's deep-sea exploration. Imagine an autonomous underwater vehicle, AUV, a robot submarine, venturing into the unexplored depths of the ocean. Navigating underwater is a huge challenge, complex currents, unpredictable obstacles, and limited visibility. Here is where the truly exceptional comes handy, noisy dueling double DeepQ networks. This is advanced DQN combined with noisy networks and enhanced exploration mechanism. The AUV's objective: find the most efficient path to its destination. The AUV uses sonar to detect obstacles, and it takes into account ocean currents. It learns through trial and error. A good path is rewarded, while collisions or inefficient routes are penalized. This robust approach incorporates noisy networks, adding a little randomness for better exploration. Imagine the AUV learning to utilize ocean currents and navigate around unpredictable obstacles, all self-sufficiently. It really is a remarkable demonstration of AI in action, paving the way for safer, more successful autonomous underwater explorations. Let's talk about sustainable energy. This involves leveraging natural resources to generate electricity, and finding the optimal nanomaterial to maximize this energy harvesting isn't easy. It's a multi-criteria decision-making problem, involving cost, durability, efficiency, even scalability. This is where DQN and Fuzzy Promethy work together. DQN learns from a massive dataset of nanomaterial properties, evaluating various choices based on diverse performance indicators. Fuzzy Promethy, using fuzzy logic to manage vagueness and uncertainty, helps in ranking alternatives and selecting the optimum nanomaterial for the specific energy harvesting application, whether it's road-based or other natural settings. This is a huge improvement over traditional methods. We're talking eco-friendly energy solutions. AI technology is leading us to better, more effective solutions for our energy and environmental needs. The remarkable thing here is not only the achievement of energy independence, but also the fact that such a technique is also being developed in this challenging field. It illustrates exactly how significant the impact of AI technology can be in solving real-world problems. Now, let's head to the city streets. Urban traffic congestion is a constant headache, right? Optimizing traffic flow efficiently is challenging, and a new approach using enhanced deep reinforcement learning is making waves. This involves using a dueling double DeepQ network and other improvements. The AI agent, within its environment, learns to control traffic signals, adjusting timings based on real-time traffic conditions that influence the network. Rewards are achieved by improving traffic flow, minimizing congestion, and reducing wait times. The agent observes traffic flow, its signal control as the action, and whether it improved traffic flow as the reward. The aim is to develop a smarter, adaptive system, responding to ever-changing traffic patterns in real time. What once seemed intractable, through the lens of DRL and its capacity to learn and improve, now becomes a highly achievable objective. We're talking better traffic flow, less wasted time, and a more manageable and efficient transportation system. Let's move on to something more fun, yet still highly challenging: a basketball shooting robot. Teaching a robot to shoot hoops successfully demands advanced technical prowess. Here, we're combining end-to-end architecture, multimodal perception, and the DQN algorithm to train this amazing robot. Multimodal perception allows the robot to integrate vision, motion, and distance data. Deep reinforcement learning allows it to optimize its shooting technique through trial and error. The robot observes the court, its throwing parameters as the action, and whether it scores as the reward. Over time, it refines its form and accuracy, learning to make precise shots, even from different distances and angles. This isn't your average shooting robot. It's a remarkable proof of how AI is propelling robotics forward, and what once felt like science fiction becomes a highly achievable objective that is being actively pursued. This application of DRL and AI extends far beyond making a basketball shooting robot and is being used for other domains that require a high degree of motor control. Let's explore another really interesting application of reinforcement learning: microgrid energy management. It's about making our energy systems smarter and more efficient. Microgrids use various renewable energy sources, such as solar and wind, to power homes and businesses. Keeping these systems running smoothly and cost-effectively is challenging, and it's all about optimizing resources and ensuring a stable energy supply. A new innovative method leverages Q-learning, SURSA, and the DeepQ network, DQN, algorithms to handle this challenge effectively, optimizing energy management, integrating renewable sources, and minimizing electricity costs. Combining DRL with other control strategies such as model predictive control and Kalman filtering also can bring in very considerable efficiency improvements. The agent observes aspects of the grid, its control decisions as the action, and whether it reduced costs as the reward. This approach significantly improves the utilization of renewable energy, reduces costs, and increases the stability of the electrical power grid. It showcases the power of RL in optimizing complex systems, such as those required for sustainability. Such an approach isn't restricted to microgrids. The underlying methodology can be applied to many power grids for better distribution and increased efficiency. Imagine a future where nearly every grid is equipped with similar energy management models for increased energy efficiency. Lastly, we'll be covering independent reinforcement learning algorithms in multi-agent environments. You might think that these environments would be best solved by algorithms that learn according to joint actions, but that's not necessarily true. Independent algorithms involve giving each agent its own learning model, ignoring the existence of other agents in the process. It sounds crazy to assume that this would work, and it is not guaranteed that this would work for all environments. However, experiments on various environments show it can work just as well or better depending on the type of environment. In cooperative environments, independent algorithms can perform. For competitive environments, such as games, independent algorithms sometimes even outperform multi-agent counterparts. On the other hand, in mixed environments where agents need to both cooperate and compete, independent algorithms fail to learn effective strategies that require coordination between the different agents. The surprising takeaway is really that independently trained agents are able to perform as well as jointly trained agents in multiple different scenarios. Furthermore, that it is far easier to scale independent algorithms than those that require learning about multiple agents at the same time. Let's delve into the world of materials science. Designing new inorganic materials with specific properties is a significant challenge. It often entails countless experiments, and this is expensive. This is why reinforcement learning is being used for inverse inorganic materials design, to design new materials with specified properties. The generator model suggests the material composition, then a predictor model provides the reward based on that and the desired properties. It's a feedback loop driving the process. The agent keeps adjusting the composition until the desired properties are met, with rewards being assigned at the end of a generation sequence. This process is repeated multiple times, and over time the model learns to produce materials that meet certain objectives. The model learns by maximizing rewards based on the predicted properties, either with a single objective or multiple weighted ones. To ensure valid chemical formulas are generated, Two different RL methods, policy gradients, and deep Q-learning are used, both of which generate various performance metrics. This innovative technology accelerates materials research, reducing time and costs substantially and increases throughput. This process is highly efficient and capable for more comprehensive exploration of the material's property space. The real-world applications of such a method aren't just restricted to material science and are extremely promising for many different fields that require high-performance material discovery. Finally, let's take to the skies with UAV formation control. This involves coordinating multiple drones to work together efficiently, smoothly, and safely. It's a complex problem, requiring precise coordination and obstacle avoidance. This paper presents a novel control strategy for UAV formation control using a deep Q-network collaborative framework. The leader drone commands a trajectory. The follower drones use the deep Q-network to learn an optimal strategy for maintaining formation and avoiding collisions. By using an MDP model framework, they adjust the actions, such as the rolling angle, based on real-time feedback and rewards. Efficient algorithms such as epsilon imitation action selection strategies are used to help the algorithm to be more efficient during exploration. Through trial and error, the followers learn to adjust their positions and orientations for safe and efficient flight. We're talking about more effective coordinated flights and improved overall success of the drone flight, which is suitable for application in areas such as search and rescue, aerial mapping, and military application. Such a methodology isn't restricted to just UAVs applications and can be used in other coordination control systems requiring multi-agent cooperation efficiently and safely.